Hello everyone, welcome back to thermodynamics subject. Today I'm going to continue our discussion about properties and how to uh, measure or characterize the properties of different substances. In previous session, we have discussed about how is the relationship between the different properties of material, how we can show the different phases of the material and the properties of those different phases of material on different diagrams like PV or TV diagram. And up to now, we uh, found that there is a relationship between different properties of a substance in each phase. So, according to this relationship between the different properties of a substance, we can assume that if we know one properties of a substance, we can also predict or guess the other properties of that substance in that phase. So why it is important? Because usually it is not easy to measure all of the properties for a substance. For example, if we know the temperature of a substance in a state, uh, if we can guess or predict other properties like pressure, like its specific volume, we can easily calculate them or easily can predict them. If we don't have any relationship between these properties, we need to measure all of these properties one by one. I mean, we need to measure the pressure, for example, in that state, the volume, the temperature, and all of the properties one by one. But if we have a good and robust relationship between these properties, then we can predict those properties just by information about the state of that substance or by just by knowing the one of the properties for the substance. So this is very useful technique to find different properties of the substance by using some other properties of that substance. Usually the property which we have are the temperature and pressure, and we can guess other properties of that material. We will see what I mean from these properties which we can predict, and we will see also the tables. We call them property tables or thermodynamics property tables, which are very important tables, not only for this chapter, also in future uh, chapters. You will need these tables to find the properties for different substances which we may have in different thermodynamic systems. So according to what I told you, some of the properties can be measured easily, so we can guess those properties which are not that much easy to be measured. And the result of this measurement and calculation can be shown in a table. So simply, if we know the one properties, we can go to that table, and for that properties which we have, find the other properties. We will see in some examples. But before I go to those tables, let me just introduce you a new properties, which is actually a combination property. It is a combination of three other properties, which we call that enthalpy. Enthalpy, or H, is equal to internal energy plus pressure of that substance in that state times its specific volume when we use this specific enthalpy. And this is total enthalpy, total energy, pressure, and volume of that substance. You see the combination property, and if you notice here, the unit for H also will be in terms of energy. U is the internal energy, and P times V, the product of this pressure times volume, also has energy unit. Simply we can see here The in the left side in this figure we have for the pressure unit for pressure, and right side you can see how it can be converted to the form of energy unit. So the unit for enthalpy also is kilojoule, or the other type of the unit for energy. This enthalpy is actually the combination of U, P, and V, which are very important properties of the material, and usually we need those properties to uh, calculate different things which we are interested to know about that system. So this enthalpy, you should notice two things about that. First, it is in one type of its unit is energy, and it is a combination property of internal energy, pressure, and volume. Okay, now let's go to the table which I told you. We have different tables, and at the end of your textbook, if you go to end of your textbook, you will see these different tables. Let me just show you briefly those tables. uh, if you go to the end of your textbook, and also I will upload, and then you will reach these tables also in these notes for the subject. However, you can find it in the uh, different thermodynamics textbooks. And this table, for example, is one of those tables. And if you notice, these tables, different table which we have, include the temperature we have, then saturated pressure, and different properties: specific volume, internal energy, enthalpy. This table is these properties, these specific volume, internal energy, enthalpy, and also entropy, which will be subject for your future chapter. But now forget about this part. You already know about the specific volume, internal energy, and enthalpy, and also about how what is saturation pressure and the temperature. So if you know the temperature of the substance, you can easily use these specific volume, internal energy, or enthalpy for that method. Vf, Vg, and these subscript Fg and or Fg, I will introduce you what are those subscripts. But the other important things about this table is for which uh, substance is that table. For example, this table is for water. So we will have, or we have actually, this table for different material or substance. This one is for the water. And also, if you notice here, it is mentioned saturated water. So to use this table, you need to know what is the state of the, or the phase of that material, and also you need to know what is the substance you are going to use the thermodynamic table for that. So this table can be used for saturated water. The state is saturated, and water is the substance for which this table is for that. And it is written temperature table. Why? Because here we have temperature as a basic uh, properties for the material. We have a similar table which is according to the pressure. And let me just show you what is that table. Table A5. If you notice here, we have pressure, then saturation temperature. Again, it is for saturated water, but this one is pressure table. Then again, specific volume, internal energy, and enthalpy. Later we will see how we can use this table to find these different properties for the material, for the water, for example, here, just by knowing the For example, here the pressure, and in this table the temperature. If we know how much is the temperature, and if we know also the state of the material, which is saturated water here, we can come to this table and find the properties for that material. We have same uh, tables for other states as well. We will see them in next slides as we go further, but they have more or less similar. Again, we will have a basic properties, then the other properties which can be found in this table according to that basic property. In different example, we will see how we can use that one. Okay, so you already know about table A4 and also table A5, which the first one, table A4, is saturation properties of water under temperature, and table A5 is for saturation properties of water under pressure. So these tables are for saturated liquid and saturated vapor states. Here is just the part of that table. You can see here the first column is a specific temperature. This is for table it's A4. We have a specific temperature, first column. Second column is the corresponding saturation pressure for that temperature, and VF, VG, for example, here are a specific volume for saturated liquid, a specific volume of saturated liquid, and Vg is the specific volume of saturated vapor. It can be Ug or Uf and Ug, which is the specific internal energy of saturated liquid, for example, and Ug, specific internal energy of saturated vapor. So we have for uh, U an internal energy, enthalpy, and also specific volume. These for saturated liquid and saturated vapor in this table, table A4, which is for a different temperature. And also we have VFG, which is difference between Vg and Vf, or specific differences between the specific volume of saturated vapor and specific volume of saturated liquid, or simply VFG is equal to Vg minus Vf. This Fg, or the difference between the enthalpy, specific enthalpy of the saturated vapor and specific enthalpy of saturated liquid, also is this one, the enthalpy of vaporization, or HFG, is Hg minus Hf. We call this latent heat of vaporization or enthalpy of vaporization, and it is the amount of energy needed to vaporize a unit of mass of saturated liquid at a given temperature in this table, or pressure, table A5. Let's see in an example how we can use these two different tables. As I told you, the main advantage of this table is to predict some properties which you have seen here, V, U, and H, by using just one properties like what we have here in table A4, temperature, or table A5, pressure. So here we have a tank. A rigid tank contains 50 kilograms of saturated liquid water. So we know what is the state, we know the mass of that, and also we know which substance it is water, and we know its temperature. Then we need to determine the pressure P and in the tank, and also the volume of the tank. Okay, simply, if we are not going to use those different tables, what we should do, we need to go and measure the pressure by manometer, and also we need to know the size of the tank to know how much is the volume of it. But we have another method, the other method, which is uh, calculating this pressure or volume of the tank by using those thermodynamics table. So first of all, the state of the substance here is mentioned. It is saturated liquid and the substance is water. The TV diagram for uh, this substance, also you are familiar with that. We had this TV diagram for water in previous sessions. In and what we are interested about to find the characteristic for that is in this point on the saturated liquid line and in the temperature of 90 degrees Celsius. So it is in the saturated liquid line. Okay, so which table we should go? We know the state, saturated liquid, we know the substance, and also we know the temperature. So first of all, we are interested to know how much is the pressure. How we can find the pressure? Since saturation condition exists in the tank, the pressure must be the saturation pressure at that temperature, which is 90 degrees Celsius. If you just go back and see the video lecture for previous session, we have already discussed about the saturation pressure. In the saturated liquid line, we have saturation pressure and saturation temperature. Each temperature has a saturation pressure. And how we can find that saturation pressure? By table. And if you remember table A4, it was for the uh, to find different properties of the saturation water or saturated water by temperature. The temperature here is 90 degree Celsius, what we have here. Then how much is saturation pressure for that? Is much 70.183 thousandths for it is the saturation pressure for this temperature. So we have the saturation pressure, which is the pressure of the water in this state and this temperature. Simply with this table, we can find that without any measurement. And then and next we are going to know how much is the volume of the tank. The volume of the tank can be, because it is mentioned the tank is full of, as you can see also here, it is full of this liquid. Then we need to find the volume of the liquid, which is water here. So the specific volume of the saturated liquid, we know a state VF. The specific volume for this state, because it is saturated liquid, it is mentioned saturated liquid. Then the specific volume for saturated liquid means VF. So we need to again go to the table A4 and find VF for this temperature. Our specific volume for this is equal to is the VF at 90 degrees Celsius. Again go to the table A4, 90 degrees Celsius. VF for this temperature is 0.0011036. Just go back. Yes, this is the specific volume of water at this state. But what we are going to find is the volume. So simply, if you remember, a specific volume was the volume of the substance divided by the mass of that substance. So the volume of the substance here is simply result of the multiplication of the mass of the substance, which we have 50 kilogram, times the specific volume of that substance, which we have here. We found that in the table. So simply the volume is this much, 0.0518 meter cube. Simply you can see here how much it is useful to use these tables. Instead of measuring the pressure, and volume for this uh, tank simply by this information. Usually we know it is the what is the state, or at least we can assume what is the state here. Saturated liquid. It's just an assumption, or it is a noun of the question. And by knowing the also its mass, we can find other properties like pressure and the volume of the tank, simply, which are not that much easy to measure. However, temperature can be only measured by a thermometer. It is much easier than to measure the uh, pressure in the tank. This is the advantages, these different calculation, and are the advantages of using of these uh, thermodynamics table. Here we have another example. In this example we are going to know how much is the volume and energy change during a evaporation process. We have a mass of 200 grams of saturated liquid water. So initial state is saturated liquid or saturated water. Saturated liquid water, it is completely evaporates at a constant pressure. So the process is happening a constant pressure process. Then we need to determine the volume change, and B, the amount of energy which is transferred to the water during this phase change process. First of all, let's see if we can draw this PV diagram or pressure specific volume diagram for this uh, process. As as you remember, this diagram, the green one is the PV diagram generally for the water, and P here is mentioned. It is constant 100 kilopascal during this process, and during this process, the phase is changed from the saturated liquid to saturated vapor. So this is the process. During that, VF will change to the VG. So initially we have saturated liquid in 100 kilopascal, and at the end of the process we will have saturated vapor again in 100 kilopascal. Let's see how we can find the volume change also and the amount of energy we should transfer to the water. Here saturated liquid water is vaporized at a constant pressure. The volume change and energy are required to be determined. The process in part A, the process is described, which is described by the question, is shown in the figure. The volume change per unit mass during the vaporization process actually is simply VFG. We have VG at the end of process, VF at the beginning of the process. So VF, just by doing this VG minus VF will give us the VFG or the volume change during this process is equal to Vg minus Vf, or specific volume of saturated vapor minus a specific volume of saturated liquid. But what about Vg and Vf? Do we have these two these properties for these two different states? Here we don't have them. The information which we have here is the pressure of the liquid, and also we know the state. We are required to know the uh, specific volume for the saturated vapor and the specific volume for saturated liquid in this pressure. Okay, then again we can go to the table A5 for this pressure 100 kilopascal. Here is table A5. The here is the 100 kilopascal pressure, and what about Vf and Vg? We have Vf here, saturated liquid, and we have also the specific volume for saturated vapor here. So we have Vf and Vg for this pressure. Simply we can use these two different values for Vg and Vf, and finally we can calculate the Vfg by this simple equation. And this is the change in the specific volume. To know how much is the change in the volume of the uh, substance here, of the water here in this process, simply we need to multiply the mass of the water by the change in the specific volume. M times we have G, we have M, we need to convert to kilogram, 0.2 kilogram times the VFG, which we have calculated previously. Finally, we have how much is the change in the volume of the water during the phase change process. For the part B of the question, we need to determine the energy which is transferred to the water during the phase change process. The amount of energy needed to apprise a unit of mass of a substance at the given pressure is enthalpy of appreciation, which I have already introduced to you at that pressure, or HFG, which HFG is equal to Hg minus HF, or simply HFG. I think it is given also in the table. So to know the Hg, HF, or HFG for this pressure, 100 kilopascal, and we need to again go to table A5. This is the pressure, which we know. This parameter, this property, very important, and we can use this because it is mentioned that during this phase change process, the pressure is constant. So Vg and Vf, both of them can be just determined by this table because the pressure for both of them is 100 kilopascal. So again, 100 kilopascal. Let's go to the enthalpy HFG and Hg. So simply you can see here we have HFG, or enthalpy of vaporization. So simply we found the HFG here in that table, in table A5, and by substitution in this equation. Why this equation? Because this HFG is for unit mass of the substance, which is, for example, kilogram here, kilojoule per kilogram. So we should multiply the mass of the substance to the this effect HFG to have the energy for that much of the mass which we have here. So zero point 0.2 kilogram times this value, 2257.5 kilojoule per kilogram, will give us the uh, energy which is transferred to the water, or required, the energy which is required to have this phase change process. So you can see again, simply by using this table A5, we can calculate the changes in the properties as well during phase change process from liquid to the vapor. The important thing about this calculation is the significant uh, numbers, or decimal digit. Here, you should note that we have considered the first four decimal digits of VFG, and we disregarded the rest. Here, VFG, we just wrote like this. If you do this, this subtraction, uh, if you calculate this by your calculator, the result will be different. It will be uh, the result will be different. Why? Because we have, here we have 246 decimal digit. Here we have only 4 decimal digit. However, you may know in the mathematics that we need to just deal with the significant digits. So we keep just 4 decimal digits here. This is because VG has significant digits number to the first 4 decimal places only. And we do not know the number in the other decimal places. Copying all the digits from the calculator would mean that we are assuming VG is like this. However, it is not like that. the accuracy of our measurement is until here. We don't know about after that, according to the table. So after calculation also we should have 4 decimal digits here even after this calculation. However, we have 6 decimal digits here, and if we write this in calculated, it will give us 6 decimal digits, but we should just keep this much, these values of the decimal point, because it is the for VG we have only 4 decimal digits significant here. So this is also important when you are going to find the VG or VF, because if you don't do this and don't consider the significant uh, numbers here or significant digits, you will have different results for this calculation. And as you can see here, the numbers are very small and it is effective on the final answer you may get from this calculation. Here you can see again just some simple example how you can use table A4 and A5 and where for which state you can use them. You can see here that table actually is for saturated liquid line, saturated vapor. You can see here VF in this temperature, VG in this temperature. For TV diagram or PV diagram, you can see again, this diagram I already introduced you, but you can see the properties for the substance in different state, and those tables are for which states. VF, VG, or other properties at the saturated liquid line, saturated vapor line, and also the differences between them can be found in the table or table 4 and table 5, table A4 and table A5 actually. Next, let's see how we can use these tables for the saturated liquid vapor mixture. This area, which includes the both liquid and vapor. Up to now, we have discussed how to use the table for the saturated liquid and saturated vapor line, or the changes between them. Then how we can find the properties, different properties, like what we have already introduced you, like energy, enthalpy, internal energy, enthalpy, and specific volume in this region. As you remember from previous sessions, in this region we have vapor and liquid as a mixture. As much as we are closer to the saturated vapor state, the amount of the saturated liquid in the mixture will be lower, and vice versa. Closer to the saturated liquid state means less vapor and higher liquid in the mixture. Then we have a fraction here. A fraction of this mixture will be saturated vapor, for example. We can use this concept and define a parameter which is quality. We call that quality, or X. It is the ratio of the mass of vapor to the total mass of the mixture. This is the important parameter to find the properties for the material or substance. And this X or quality is a number between 0 and 1, as you may guess. When we have saturated liquid, it means no vapor in the mixture, this X will be 0. Simply by this equation, you can guess that if X is 0, it means we don't have any vapor, so we have saturated liquid. And if we have only vapor, then M of vapor will be equal to total M, which is the summation of mass of vapor and liquid. And total is M liquid and plus M vapor. And if we have If X is 1, it means M vapor is equal to the M total. So it means we don't have any liquid. If X is 1, we have saturated vapor only. Then the properties of the saturated liquid are the same whether it exists alone or in the mixture with saturated vapor. In other words, the properties of liquid, the amount of liquid which we have, and the amount of vapor which we have, the properties of those two are still those properties which we have for that when they are in their saturated liquid or saturated vapor or on their lines. So when they are in the mixture, we can simply assume that however they may have be like this in two different phases, saturated vapor and saturated liquid, not mixed completely and homogeneous to each other, but we can imagine they are in the homogeneous mixture instead of these two phase mixture. We can imagine we have a homogeneous mixture of saturated liquid and vapor. Then we can define an average for different properties. For example, we may assume we have V average or specific average, a specific volume for this mixture. Average, or you can have for U, for H. So for other properties also, we can assume we have an average of those properties for this. Then how we can calculate these average properties for this mixture? Let's see how we can calculate that. This V average can be calculated by this equation. V average plus the V average is equal to Vf, specific volume in the saturated liquid of the saturated liquid, plus X, which was the quality mass of the vapor divided by mass of the total mixture, times VFG, which also can be found from the table or simply by the equation which I shown to you, Vg minus Vf. So V average, which is the specific volume for the mixture, can simply be calculated by this equation. And also for other properties, we can have same uh, equation. This is for V, for U, for H also we can have that. And simply you need to just memorize this. Y is the property which can be V, U, or H, which is equal to that property saturated for saturated liquid plus X times the for the uh, Fg of that property can be V, U, or H. And this property will be the amount of this each one of these properties will be between the values of that properties for saturated liquid and saturated vapor of that substance at that temperature or pressure, or simply like what you can see here. This is P or T V diagram. They are identical. The diagram is identical for both of them. And you can see what I told you here. For example, we have Vf here on saturated line. We have Vg in unsaturated vapor line. Then V for mixture, which is a mixture of these two. For example, this is a constant pressure or a constant temperature for different PV diagram or TV diagram. Then we have Vf, we have Vg, but we don't have the V specific volume in this area or this region. It depends on the place of this state. As much as closer to Vg, the value will be closer to Vg. I think closer to Vf, the value for this V for mixture is closer to Vf. But it is always between these two values. It is same for HF, HG, UG, or UF in these two different states. And this is also U average, V average, and H average as well. And sometimes we may do not have this Mg or Mt. We may have only the Vf and Vfg. How we can have these two? If, for example, the pressure is given and we know how much is the pressure, for example, or temperature, we can go simply find this. And sometimes we need to calculate x by this equation. If just restructure this equation, x will be equal to V average minus Vf and Vfg. And if we know how much is Vfg, V average, and how much is Vf, how much is Vfg, we can calculate x. This x can be used to calculate other properties as well. So this is another method to use these equations and x to find different properties for a substance. Simply, if we have all of this information, we can calculate x. Then by using this x, we can calculate other properties which we have. And this is the illustration of this equation. Actually, why we have this equation for x. Simply, as I told you, we have this pure TV diagram. We have two different states, A and C. We know how much is the specific value for them, but we don't know how much is the specific value for state B, which is between these two on a constant pressure process or a constant temperature process, or same pressure and temperature here. Then how much will be the V average? Simply, you can see here. Uh, Here this amount is V average. Here V is V average. So this amount is V average minus Vf, and all of that is Vfg. Simply, so x is AB divided by AC. This is the definition of x, which we use this illustration to derive this equation to find x. This x means how much is the vapor and how much is the liquid in the mixture which we have. And here is just some example of what I told you. Here, for example, we have 8 kilogram of liquid, 2 kilogram of the vapor or gas here, and we know how much is the temperature, 90 degrees. So simply by this information, we can calculate x. 2 divided by 10, 2 plus 8. Then we have x, we can calculate Vf and Vg for this. We are going to understand V for this one. How much is it? We need to first calculate x. By this information, we can calculate x, then use that equation which we had in previous slide. We just showed you. The average Vf plus Vfg. We have x, we have Vg, we have Vf, then we can calculate Vg minus Vf, which is Vfg. Then simply we can use this equation to find the average for this point. And same for other materials, other substance, also for R134A, it is a type of gas, also another material which is usually being used in different refrigeration or air conditioner uh, equipment. We have also thermodynamic properties table for this material at the end of this textbook. The procedure to use that table also is same as for what we have for the water. Let's see an example about this what I told you now, how we can use this X or quality concept to find the properties of the substance in this mixture region or saturated vapor and saturated mixture actually. We have a rigid tank contains 10 kilograms of water at 90 degrees Celsius. So we know how much is the total mass and we know how much is in 90 degrees Celsius. And if 8 kilograms of water is in the liquid form, so from this sentence, this start of the sentence, we know that we have a mixture. 8 kilograms of water is in liquid form and the rest is vapor form. The rest means 2 kilograms is vapor. Then we need to determine A, the pressure in the tank, B, the volume of it. Simply again, you can see here we have temperature and we have the mass. But here, because we have a mixture, we need to also find X or quality. If we show this state which is mentioned in this question in a TV diagram, it is something like this. You know, the green line is the general line for the TV uh, for the water, saturated liquid, saturated vapor, and in this temperature we know 90 degrees Celsius. Then it is like this. Uh, 10 kilograms of water, 8 kilograms of water is in liquid form. However, I think this point is not correct. This should be closer to the uh, mm, uh, no, how it is right. Sorry about that. It is right more closer to the liquid or saturated liquid line. You can see here more liquid or moisture we have here. So we know about this point, temperature 90 degrees Celsius, and we know the mass of vapor, we know mass of the liquid as well, or mf. First, we need to, because it is mentioned, we need to uh, find the pressure in the tank. So since the two phases coexist in equilibrium, we have a saturated mixture, and pressure must be the saturation pressure at the given temperature. It is also, according to the information which we have discussed in previous session, when we have a mixture in two phase coexist in equilibrium condition, then again we should have the pressure should be saturation pressure for that mixture. Again, like what we had also in previous example, we need to refer to table A4 for this temperature, 90 degrees Celsius. Again, find the saturation pressure, which was or which is 20 point something kilopascal. So we know how much is the pressure. What about the volume of the tank? At this temperature, we have VF, we have VG, both of them from the table. It is like what we had before. In this temperature, we have VF. In this temperature, 90 degree, we have VF. We have VG as well. So simply, uh, we have VF, we have VG. We have two different methods to find the uh, volume of the substance or mixture. First of all, one way of finding the volume of the tank is to determine the volume occupied by each phase and then add them. Like here, V is equal to Vf plus Vg, or the volume of fluid or volume of the liquid plus volume of gas or vapor here, which we know that volume of fluid is the mass of the fluid times specific volume of that fluid, or mass of gas times specific volume of that gas. We have Vf, we have Vg from the table. Mf and Mg also is given by question instruction. Then finally, we can easily find the V or the volume of the mixture here. This is one method. The other method is to use XOR quality. We can calculate X, if you remember, we had this equation for that. Mass of the vapor divided by mass of total mixture. Mg divided by Mt, 2 kilogram. Mass of gas, 10 kilogram of mass of total of the mixture, then it will be zero point 0.2. Then we can use this equation to find V or specific volume of the mixture. V equal to Vf plus X Vfg. We have Vf here, we have Vg here, and we have calculated X as well. So simply by substitution of the value for these properties, these parameters, we can find the specific volume for this mixture. Simply, finally, we can multiply the mass of the mixture M, but in kilogram, notice here, M should be mass of the mixture because this V which we have calculated here is specific volume for the mixture. And we have V, then we can have the volume of the mixture in the tank. As you can see here, we can use both of these two methods to find the volume. You can see the result will be same. However, usually it is not that much easy to find the this property. For example, without using X. Later we will an example because usually the masses which are given here are will not be given to you to calculate the different properties of substance, and you need to use these X to calculate those properties. In this example, we will see how we can use the table, the properties table for different substance. Here the substance is different. Is refrigerant 134A, which is an important refrigerant. And also we will see how to use that X when we don't have enough information to use that simple method just simply by using the mass of the substance. We could determine the properties which was a specific volume in previous example for the substance which we had. So here we need to we will see how to use that X. In this example we have a vessel. We know how much is what its volume. It is 80 liters, and also it contains 4 kilogram of this refrigerant, and the pressure of the refrigerant also is given, which is 160 kilopascal. Then we need to determine the temperature, the quality, which is X, the enthalpy of the refrigerant, H, and also the volume occupied by the vapor phase, or V of gas actually. So this is a schematic for the what we have here. However, the information which you can see here is after calculation. So first, let's solve the problem. Later, we will again refer to the schematic. Part B, the state of saturated liquid mixture is shown in this figure. Later, we will refer to that. However, according to the question, we should guess the state. With this information, we do not know whether the refrigerant is in the compressed liquid, superheated vapor, or saturated mixture region because it is not mentioned. If you remember, in this diagram, we have compressed liquid here, mixture region here, superheated region here. But here, according to this information, we don't know in which region we can find information for, or in which region is the state of this substance. How we can determine the state or region which this material with these properties is located? This can be determined by comparing suitable properties to the saturated liquid and saturated vapor value. So if we have a property of this substance which we can compare with this the properties for that substance in these two lines, we can understand if it is in the superheated region or in the compressed liquid region or even in the mixture. From the information which we have here, we can determine the specific value, which is a properties of material. We have the volume, which is given 80 liter. We know the mass, it's 4 kilogram. So the specific volume here is 0.02 uh, cubed meter per kilogram. So we know how much is the specific volume. So we define the properties. As I told you, if we have one property and we can compare that with, this is the average actually. This is we have. Then we need to, this V is for this substance in this pressure. So P is 160 kilopascal and V is per kilogram. But still we don't know in which region is this state. I mean this point which is already shown here, we don't know where is the place for that. How we can determine that? First, let's see if we can find this information for V specific volume for the saturated liquid and saturated liquid. We have table again for this refrigerant, thermodynamic table or thermodynamic properties table actually for this refrigerant we have that. For this pressure 160 kilopascal, we can refer to the table which is table A12. So just remember the pressure 160 kilopascal, which is table A12, saturated refrigerant 134A pressure table. The pressure which we have here is 160 kilopascal. You can see here we have here this is the pressure which we have here. Here is the saturated temperature, and also we have Vf, we have Vg. So we just should record these two values, and again go back to the question. The V which we have calculated is 0.02, and you can see here Vg is a point 0.12 something, and Vf is just much lower than 0.02. So this V is between these two. So V which we have is between these two. So the state which we have is in the mixture area, is in the saturated liquid and vapor mixture area. It is how we found that by comparing the properties which we could calculate by the information which was given by the question, by the information which we can get from the table. So obviously the refrigerant is in the saturated mixture region. Then also I showed you the saturated temperature. For this pressure we can find this saturation temperature as well, which is negative 13.60 degrees Celsius. So we first of all we found the temperature which was given by the question. Again, like before, that's the temperature of the mixture should be saturation temperature because we have a equilibrium mixture which both of two liquid and vapor are in equilibrium and coexist in a a mixture. Part B is the quality or X. How we can find X? If you remember, I introduced you this equation to find X. X equal to V minus Vf divided by Vfg. We have V, we have calculated here, we have Vf, and Vfg simply we can write Vfg is Vg minus Vf. We have both of them, simply substitute them here. Then we can calculate X or quality. The answer for part B. Part C, the enthalpy of the refrigerant. Simply again, as I told you, we have this equation by knowing the quality, which we have calculated here, and the HF and HFG, we can calculate enthalpy or H average actually here for this state by this equation. But we have X here. How about HF and HFG? Again, we can go to table A12 for this pressure. We have HF, HFG, and also HG. So we have all of these properties as well. Simply by substitution, we can have finally enthalpy for this state. Part D is the volume occupied by the vapor phase. According to the equation which we had for the quality, we had this equation xmg divided by mt. Just by restructuring of this equation, we can write mg is equal to x times mass of the total mixture. We have mt, it was given 4 kilogram, and also we have calculated x 0.157 or 157 thousandths, and by substitution we can have this mass of the vapor in this mixture. If we know how much is the mass of the vapor in this mixture, simply because we know how much is the Vg for this refrigerant, we can use this mg and Vg, which we have from the table, and we have mg, we have Vg, then we can calculate. We have a specific volume for saturated vapor or Vg, and also mass of the vapor or gas here. Then by multiplication of these two, we can find the volume of the substance or refrigerant which we have in this vessel, which is this much or 77.6 liter. As you can see here, the volume of the gas is 77.6 liter. Then according to this equation, we have liquid is V minus Vg. We have V total is 80 liter. Here we have that minus this volume of the vapor. Then we will have 2.4 liter for the volume of the liquid. Simply, you can see we can use that thermodynamics table to find the volume and also other properties. And you can see here how much X or quality is useful parameter to calculate different properties for this material, and the combination of these X or quality by the table is very useful method to find the properties for the different material in different states. Next, we will see about other region. Up to here, we have discussed about saturated liquid, saturated vapor, and also the mixture. We will see about superheat and compressed liquid region, what are the tables for those two regions.